This will be sort of a sequel to the talk that Alessandro gave the other day, but I'll try to make it self-contained the way we just made that talk. So let me start by reminding people of what asymptotic dimension is. So the idea is to generalize sort of dimension theory to something that will work in the context of coarse geometry, so we can think about it as finally generated groups. And so if we kind of recall that there's a bunch of different equivalent definitions of what a topological dimension is, and one standard one is that a space, the one that works in a metric space, is that the topological dimension is at most n if you can find a covering by a bunch of sets, each of size, a bunch of open sets, each of diameter less than epsilon. And then, given that collection of sets of diameter less than epsilon, you can partition them into n plus 1 collections, where inside each of those collections, everything is pairwise disjoint. So if you satisfy that, then your dimension is at most n. And so there's a bunch of equivalent definitions of asymptotic dimension. The one that I want to start with is just the large-scale analog of that. So you need to replace, diameter less than epsilon by the diameter, and you need some replacement for what it means to be disjoint, and we'll talk about sort of being distance larger than a certain value. Okay, so here's the, so let me start, before I say what the dimension is, let me start with the zero-dimensional version. So we say that a metric space X is disconnected, or has dimension 0, so disconnected at scale R, if it satisfies the following property: if X is a union of a bunch of subsets, if X is the union of a bunch of UIs, such that we have two conditions. So one is, there exists some constant, so we want a replacement for everything being diameter less than epsilon. There exists a B such that for each I, the diameter of UI is less than B, so they're all bounded diameter sets. And the second one is for each ij, the distance between UI and uj is bigger than R. So you think of having a bunch of sets that all have some diameter some diameter bounded by some uniform constant B, and those sets may be big, they may be size B, but they're all kind of distinct from each other. They're all far apart from each other. So that's what it means to be disconnected at scale R, or dimension 0 at scale R. And so now what we want to do is we want to generalize that to something that will work for a dimension. So actually, maybe I'll give you an example of this first. So let's think about the integers, which is our simple example. And so we can say that Z is disconnected at scale R for any R less than 1. So if we have a small enough scale, then you just cover by these points, and they're all kind of pairwise distance one away from each other. And so for any scale less than R, we're disconnected at that scale. But somehow but for larger values of R, right? If we want to care about large scale geometry, we need to not care about some sort of uniform bounded scale. We need to know what happens as scales get bigger. And this is not disconnected on scales bigger than 1. So to fix that, we kind of soup up the definition, and we say X, so a metric space X, has asymptotic dimension n. But asymptotic dimension, I'll say at most n. If we can decompose it into n plus 1 sets that are each disconnected at scale R. So if for every R greater than 0, there exists a B greater than 0, such that in families U0, U1 up to UN, where each which cover X and which are each disconnected at scale R. Scale R. And at scale R with respect to this uniform constant B. Okay, so this is what it means to be disconnected at scale R. And so let me just do, so I find it hard to see on this blackboard, so I'm just going to try and draw pictures on the bottom blackboard. And leave the writing to the top blackboard. So okay, let's go again to Z. So the asymptotic dimension of Z is equal to 1, because for any bound you give me, right, I can find, for every R you give me, I can break it up into sets. So maybe I'll put these 3 vertices together, and these 3 vertices, and some other 3 that are out there, and some other ones that go out this direction. And there's my set that's a bounded diameter, and these yellow sets are now disconnected at scale 3, and the blue sets, right? These are each now the blue sets decompose into a bunch of sets which are each bounded diameter, and which is also the blue sets together are disconnected at scale 3, and we can do this for any R we want. Sort of break it into alternating clumps of R vertices, and we see that we've got now 2 sets which are each disconnected at whatever scale we want. And so therefore, the asymptotic dimension of Z is equal to 1. Okay, so that's sort of the motivating simple example. And so maybe I'll write a few basic facts here. So a few basic facts are the asymptotic of Rn is equal to n. Okay, so that's not, it takes a little bit of work to prove it, it's not that hard. But it's not meant to be a deep theorem. It's just sort of meant to tell you that this is recording it's recording the sort of information that you think it might be recording. So this dimension is the right level. And the nice thing about the way we define it is it's not hard to prove that ASCIM is a QI invariant. Okay, so if we care about finally generating groups, then this is sort of a natural invariant that we can associate to our group. Okay. So what I want to focus mainly on examples. Let me just mention a few results that motivate why some people think about asymptotic dimension. I'll put it on this board. Put this board up. So some motivation is. So Blowing U proved several theorems about asymptotic dimension, but he proved things of the form that if you're finally presented and you have finite asymptotic dimension, and you have a classifying space that's homoscopic equivalent to a finite CW complex, then you satisfy the Knopfrock conjecture. So sort of finite asymptotic. The so hypotheses implies the Knopfrock conjecture. For that group. Similarly, if you have finite asymptotic, you also proved another theorem that you get, of course, Baum-Kahn conjecture. Baum-Kahn conjecture. So if you care about these kind of classical conjectures in topology, then there's relations that finite asymptotic dimension tells you about those things. There's theorems of Grunichnikov. Where if you have finite asymptotic dimension and you have a space which is like uniformly bounded, so if you have a calligraph of a finally generated group, then for instance you know that you embed in a product, then you coarsely embed in a finite product of trees, product of finite valence trees, product of trees, and you get an explicit bound, so it's 1 more than the asymptotic dimension. You also, so another theorem of Grunichnikov is that if you have finite asymptotic dimension and you have some uniform boundedness on the valence, so if you have a graph, then you get a coarse embedding into a non-positively curved manifold, NDC manifold. And you get an explicit bound there on what the dimension is of that manifold, depending on what the asymptotic dimension is. Okay, so I'm not going to talk more about those applications, but those are kind of there if you want to explore this further. Okay, so what I do want to talk about is some explicit examples. So let me mention some known cases. So some known cases with finite asymptotic dimension. So even for our n, it takes a little bit of work to prove that the asymptotic dimension is equal to n. So you can imagine that things get hard fairly quickly. So some of the most classical results on this are, well, the first one was for hyperbolic groups. So Gromov proved that any hyperbolic group has finite asymptotic dimension. So that gives a finiteness statement. But then there's a stronger statement of, well, if I wanted to get bounds on what the product of how many products of trees I embed in, or what's the dimension of the non-positive curved manifold I embed in, then you might want to get stronger bounds on what the asymptotic dimension is, and not just know it's finite. And so in that case, there's theorems of so like an explicit bound. So for instance, in the torsion-free case, or in the virtually torsion-free case, then the asymptotic dimension is equal to, so for a hyperbolic group, is equal to the virtual cohomological dimension, and that involves a theorem of SVMS and another theorem of Borello and Lebedev. Okay, so that was sort of a much harder thing to actually compute or to get bounds on what the asymptotic dimension was. So another case that involves a family of groups that we haven't heard that much about yet at this conference, but that are much studied, are writing Coxeter groups. Okay, so finiteness there was proven by Davis and Januszkiewicz. So Davis and Januszkiewicz, they proved that for writing Coxeter groups, you get some bound on the asymptotic dimension, and they proved that by just proving that you embed some product of trees, but they didn't get explicit bounds, and so there's better bounds, but in fact the bounds aren't known in general, but there's better bounds that were provided by Nick Wright and by Behrstock. So for various classes, you can get sort of some more explicit bound, but nothing's known in general. No sharp bounds are known in general. And then there's another family that we're interested in because it's kind of a generalization of hyperbolicity is relative hyperbolic groups. So if you're hyperbolic relative to a group to finite asymptotic dimensions. So finite asymptotic dimensional subgroups. So Dennis Osen proved that implies that you have a bound on the asymptotic dimension. And then the last class, the main one that we want to focus on today, is for mapping class groups. So if the mapping class group of a finite type surface, then Vespina, Bromberg, and Fujiwara they prove finiteness, and if you want to get a more effective bound, then the right thing to do is try to measure what the bound is in terms of the complexity. So I'm going to write the complexity of S is 3 times the genus plus the number of punctures 3G plus P minus 3. So this is the complexity, or the topological measure of the complexity of a surface. So their bound, the original finiteness bound they get they don't compute it, but it's something like double exponential in complexity. And so then they worked to improve that, and so Behrstock and Bromberg improved that slightly, so they improved the bound to something of the order e to the complexity of s. Okay, and that was sort of the status when we started thinking about this. So one of the main theorems I want to focus on today, get into Cisco, is so we proved that, that the asymptotic dimension of the mapping class group of S is at most, I guess, 5 times the complexity of the surface squared. So we improved it from an exponential bound to a quadratic bound. And should it be linear? So the conjecture, the conjecture that is that in general, anytime you have a finite asymptotic dimension, it should equal the virtual cohomological dimension of the group. But no one's been able to prove that even for writing a Cox group. That's not known. Even for writing R groups, I think that's not known in general. So there's a conjecture that one might be able to bring it down to linear. But we don't know. Okay, so what I want to do today is I want to talk about this theorem, but really I want to talk about sort of a more general context in which we prove this theorem. So we prove this theorem by proving a more general theorem, and that more general theorem is interesting because not only does it prove this case, but actually it proves all these other cases all at one time. Not only does it prove all these cases, but we do so and we get kind of very good bounds, sort of at the same time as proving a very general result. So let me now sort of change gears for a little bit and tell you about what hierarchy hyperbolic spaces are. Hyperbolic spaces. So Alessandro gave an introduction to these the other day. So I'm going to repeat some of it, but do it in a slightly different way. So this will help sort of help everyone hopefully understand these spaces better. So what are hierarchy hyperbolic spaces? So in general, they're built out of. So I'm not going to give you the full definition, but I'm going to tell you the relevant part of the structure. So there's some space X, which is a geodesic, quasi-geodesic metric space. And maybe let me simultaneously tell you what this is in the case of the mapping class group. So Wolf, maybe up here in red, I'll tell you what the structure is for a particular space, so we'll think about the mapping class group of a surface. Okay, so we have the space, then we have another set, which we often denote script S, which is so this is our index set. I'll tell you what it's indexing in a minute, but that index set, in the case of the mapping class group, is the set of essential subsurfaces of S. So pi1 injective subsurfaces of the original surface. So you've got a surface, and then you've got a collection of all subsurfaces, and that's going to be our index set. And what is that indexing? We're going to also have a set which we'll denote in general script C of W. And here W is going to run over script S, and these are going to be delta hyperbolic metric spaces. They're geodesic metric spaces. Okay, and in the case of the mapping class group, unfortunately we have the exact same notation, but it's a familiar object in that case. So these are the curve graphs of S and its subsurfaces. Okay, and so this is maybe I'll take a brief aside and ask, does everyone know what the curve graph is?
Jason, can you write slightly larger?
What?
Can you write slightly larger?
I can write slightly larger. But
Thank you.
should I define what the curve graph is? Who wants me to define it? I'm happy if there's even one person. Okay, so I'm happy to skip it also then. Okay, so everyone, this is great. Everyone knows what the curve graph is. So the classic curve graphs are these delta hyperbolic spaces that we care about. And so these are the family of hyperbolic spaces which are going to encode all the geometry of the original metric space. And I should maybe just briefly say, just as a kind of an aside, there's a slight generalization where they're not all delta hyperbolic, some of them are not, and that allows us to form a relatively hyperbolic space. And for those, the same theorems go through, and that's how we can also get to the hyperbolic case. But I'm not going to say more than that about that now. Okay, so these are the kind of the spaces that we care about: the metric space, the index set, and then the things that it's indexing, these delta hyperbolic spaces. And then there's some auxiliary structures. So S has a partial order. Order, which is denoted by a square nesting sign. So in the case of the mapping class group, so for MCG, this is subsurface inclusion. Okay, so this relation in general is going to generalize the nesting relation in a surface, and in general we call this nesting. So that's going to be our partial order, and there's a couple conditions on that. So one property that this has is that in general, so we're going to assume in the general case we assume that there exists a unique nest maximal element. In the case of surfaces, this element is the whole surface S, right? Every subsurface nest inside the whole surface. Okay, so there's in general a nest maximal element as long as the index set is not empty. Okay, and then we have another relation. So there's so S also has a symmetric anti-reflexive relation called orthogonality. And denoted by this perpendicular sign. And in the case of surfaces, in the case of the mapping class group, this orthogonality is disjointless. Okay, so two subsurfaces are orthogonal if only if they're disjoint. Okay. Right. Alessandro also mentioned that there's a transversality.